Hey everyone, welcome back with a new lecture with quality control for chemical analysis. In the previous lecture, I have said that quality of data refers to the accuracy of results, which is inverse to errors. So the highest the errors, the lowest the accuracy. You need to control the errors during development stage to get high accuracy. You need to control the errors to be within acceptable limit. At the end, you will get valid results also within acceptable limit. But quality control cannot eliminate or reduce the errors, but that you can do only during the development stage, and after that in quality control you need to evaluate the errors only. And if you have after that any problem, you should go back to the development stage. So this lecture inshallah and also the other lectures, next lectures will be around errors. Errors in analysis refers to deviation from the true value or expected value. So the difference between expected value and the practical value will give you the errors that you have in your analysis, and classified into different types based on their causes and effects. We have systematic and random errors, which are the common errors, and also we have gross errors and human errors. All of them will be explained in details, and I will add also some case studies for each one to be clear for everyone. First type, which is systematic errors. Systematic errors, consistent and repeatable errors. So it will be repeated every run. And because of what? The causes for that: instrumental errors, method errors, and also operator errors. First one, we have instrumental errors. Systematic errors because of the instrument. So these errors will be repeated every run, and it will affect every run on the routine samples. Instrumental errors such as calibration issues, poor maintenance if you don't have regular maintenance, uncalibrated equipment such as balance or pH meter or micropipettes or other equipments also. First example, we have calibration issues. Calibration issues because of expired or degraded standards. So the issue is calibration of your instrument. There is a problem with calibration because of degraded standard. If you have standards, degraded standards, the concentration of prepared standards or prepared calibration standards will be lower than the normal. So the response also will be lower than the normal. If you will prepare different calibration standards from the stock which has been degraded, so the concentration of the stock will be lower than the normal. If you have 100 ppb or 1 ppm, 1 milligram per liter, it will be lower than the normal. So prepared standards also will be lower than the normal, and you have relation between area and concentration of the standards. If you prepare, as example, 1, 5, 10, 25, 50, 100 microgram per liter or ppb, and you got very good calibration curve and slope is accepted, everything within acceptance criteria, because if the concentration should be 10 ppb and the area should be 100, so this concentration became lower, became 5 ppb as example after degradation, and the area became 50. So everything is same for each standard, so the calibration will be accepted within acceptance criteria, but it's not the real concentration for each one of them, and that will affect also the concentration of target analytes in the unknown sample, and I will explain why with that now. As you know that calibration used to quantify the concentration of target analytes in the unknown matrix or unknown sample. So you will prepare different calibration standards, and the instrument will create calibration curve containing these concentrations, and you will have the relation between the area and concentration of your calibration standards. These calibration standards, as I said, 1, 5, 10, 25, 50, 100 ppb, 100 microgram per liter. And your sample will be compared to this concentration, because your sample results also should be in between these calibrations to be quantified. So your sample concentration or target analytes in the sample will be compared to these concentrations. As example, if you have target analyte concentration should be 10 ppb, it will have the same area of 10 ppb. This is 10 ppb and this is the area 100 as example. So it should have the same area. It should be at this point. It should have the same area. In the sample also should be also 100. So 100 means 10 ppb or 10 microgram per kilogram in the sample. But if the concentration of standard is lower than the normal, also the sample concentration will change, and the equation used for quantification of sample concentration or target analytes in the sample by the instrument is sample concentration equal to area of sample divided by area of standard multiplied to standard concentration. So if, for example, the area of sample is 150 and I will use the concentration, standard concentration 10 microgram per liter, and at this concentration the area should be or was 100. So you have it equal to 150 divided by 100 multiplied to 10, which is equal to 15 microgram per kilogram. This is the sample concentration should be. The target analyte in this sample should be 15 microgram per kilogram. But if the standard has been degraded, the sample concentration will be equal to this one, or area of sample, still 150 because not degraded, but the standard has been degraded from 10 to 5 as example. So the concentration here, the area of standard here became out 75, and the concentration standard is 10. So it will be 20 microgram per kilogram. So the concentration of sample changed from 15 to 20 microgram per kilogram, increased. By degradation of standard, the sample concentration increased, and that will be every run. So this is systematic error because it will happen every run for all samples analyzed. So you should control this, and I will explain also how can we control these errors. For sure, in the previous example, to solve this issue, systematic error due to calibration issues because of degraded standards, you should run quality control samples every run to know that there is an issue like this, and then you will buy new standards to fix the issue completely. But all of this will be explained after in the next lectures, inshallah. Also, another example for method errors. Method errors such as matrix effect. Matrix effect is there for some matrix which is hard, such as food or whatever, or blood or whatever samples. So we need to fix this issue. In development stage, you should find the method. You should try to eliminate or reduce the effect of matrix interferences on target analytes, because it will enhance or decrease the concentration of target analytes, and maybe that will affect the accuracy of results. So you should try to eliminate or reduce the effect of matrix interferences on target analytes during development stage, such as you can change in the extraction solvent. You can add extraction solvent, adding another formic acid or acetic acid to change the pH of the medium, because that will be maybe suitable for your target analytes to be extracted. You can change the pH for mobile phase. You can add also another chemical to maybe, as example, in case of tetracycline compounds, there is a chelation between tetracycline compounds and the heavy metals, trace metals found in the sample, in chicken or meat or whatever. So you need to remove or stop this chelation. So you should add EDTA to stop chelation between tetracycline compounds and heavy metals, because EDTA will react with heavy metals, then tetracycline compounds will be extracted alone without any other interferences. So you need to add any other chemical to fix this issue. So you have many things to think about during development stage, but at the end you need to eliminate or reduce the matrix effect. So if there is still matrix effect after you develop the method and you have final method approved, then still there is matrix effect. This matrix effect should not affect the accuracy of the result. And to fix this issue, you have three things you can do: matrix matched calibration curve, or you have also internal standard. You can use internal standard, or you can add another sample which is standard matrix sample. And all of these will be explained after, inshallah, in quality control procedures. As we have here in this example, if you spike the blank sample with 50 microgram per kilogram and you got on the instrument 20 BBB, so recovery in this case equal to 40%, which is not accepted. So here in this case there is effect of matrix interferences on target analytes by suppression. It decreases the concentration of target analytes, so you need to eliminate or reduce this effect, and that will be by three ways, as I said before: by preparing matrix matched calibration curve, preparing the calibration standards on the sample itself, on the blank sample, or using internal standard, or you can add one more sample which is a standard matrix sample. All of these ways will be explained after that in this training course in details. But for now, you should know that systematic effect will happen every run, will affect every run. It's consistent and repeatable until you fix this problem. And in the next lecture, inshallah, I will explain some case studies relating to the systematic error, and after that we will go for the random error and gross errors. Thank you, and see you in the next lecture, inshallah.